Hey guys, Dash Arrives here, and today I'm going to be going through this H3 Physics 2019 paper. So here's my email. Feel free to contact me if you want free math or physics help at any level you want. And I'll be going through this paper, but because I'm actually still a student, H3 student, I'm not a teacher, I'm not a qualified teacher. So if there's any errors that I make, please refer to the description, and please raise up any possible erratas that I might have said, um, so that I don't end up teaching the wrong content and confusing you guys even more. But anyway, I'll be going through this paper, but along the way I'll be lecturing about some related concepts hopefully, and as a result I'll be taking much more longer than the 1 hour 50 minutes written in this paper. So how it's going to go is that I'm going to answer the question. So for example, in this case, sketch the planet's orbital motion according to Kepler's first law. So I'll be answering the question. So this is ellipse, and then I'll say that I'll just be answering the question like that, and 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 then after that I'll write some related concepts. So in this case, the semi-major axis is defined as this horizontal part of the ellipse, the bigger part. So then I'll be name dropping certain related concepts such as bound or unbound orbits. So this is just an example as we dive into the first question. Okay, and then after that I'll be talking about ellipse properties, let's say. So yeah, and of course I have to balance between focusing on the paper and talking about related topics. So please forgive me if I miss out certain content, or if I spend too much on extra content. So yeah, so let's begin the paper. I'll probably end up splitting this paper into a few parts, because if I'm going to digress quite a lot, then it's going to take a long time. But at the end of the day, the goal is to provide free consultation and educational content, and yeah, and moreover, please feel free to message me or email me. Don't be embarrassed. I'm here to help. Yeah, now that I'm more free, I want to help as many people not struggle with physics as possible, physics and math. So yeah, so okay, sorry I keep on saying yeah, but let's begin. So we have done the first question. The planet's orbital motion is an ellipse, okay, and Kepler's first law, Kepler has 3 laws. So they give rise to uh, certain rules, such that Kepler's first law, I believe, if I remember correctly, is that the area swept out by the object it is constant over time. So for example, what that means is that when the object is near the Earth, right, then when it sweeps out, it moves at faster velocity. So when the object is near Earth, it moves at faster velocity, and it sweeps out some area, whereas if it's further away, right, it moves at, okay, that's a bad drawing, it moves at slower velocity, slower, and as a result, the area that it covers per unit time, so it's going to be the same over time. So yeah, yes, so we could express it in terms of, okay, I'll not go into that lah, but that's Kepler's first law. So what do I have to talk about? Bound and unbound orbits. So for bound orbits, so as a result of laws of gravitation, there are several ways an external object can interact with a massive body. So for example, this is Earth, right? And let's say we send a satellite, or let's say there's a piece of rock. So there's a rock that flies around, and it'll be influenced under Earth's gravity, right? Of course. And assuming Newtonian gravity, which means it's GMM over r squared kind of force law. Okay, so this Newtonian gravity. Assuming Newtonian gravity, there are a few ways that this rock could behave, and it depends on and the easy way, so let's classify the ways that this rock could interact with the object. The first way is bound. So okay, I just realized I probably need more space. I have an idea. So okay, I'll just do this. Okay, I have this blank sheet of paper over here that I'll be writing on. So bound, there's bound unbound orbits, bound unbound trajectories. So first idea is bound. So if the total energy is less than if the total energy is less than 0, okay, sorry, I'm so sorry. I gotta fix this thing. Okay, if the total energy is less than 0, then it's bound. And if the total energy is greater than 0, it's unbound. So you might be wondering why is that so? So you think about total energy is actually equals to Ke plus GPE, right? So if KPE plus GPE is less than 0, that means that yeah, so that means that KE and GPE is less than 0. And what might that imply? So when it's bound, the object essentially it travels around Earth, and it will always be confined within some region of space around Earth. Basically, it will never fly out to infinity. Whereas when it's unbound, you cannot draw a box around the object's trajectory, meaning that you'll fly in and then you'll fly out and it's gone forever, it's gone to infinity. So it's to infinity. And it comes from infinity, infinitely far away, and it goes to infinity. So what's one easy way to see this is that we know that GPE is negative, right? So and we also know that GPE is 0 at infinity. So with these two facts, we realize that the closer the object, right, because the GPE is minus GMM over R, the closer the object, then the more negative the energy, the GPE. And because GPE plus KE is constant, so the KE will be more positive, and as a result, the object is faster. So you see, by energy considerations, we can already figure out that the closer the object is to Earth, right, the faster it is when it's flying under the influence of Earth's gravity by conservation of energy. So that kind of explains this fact just now that we had over here as well. So yeah, so okay, this is one thing to note. Another lesson to take away is that what is the mean? How do you know whether something is bound or unbound? It actually completely makes sense with this, whether GP is negative or positive, because you see, in the bound case, right, if at infinity, GPE is 0, so KE is less than 0. And this doesn't really make sense because KE is always positive, so doesn't make sense. So this doesn't make sense. So what makes sense then? It makes sense if in the case of unbound orbit, which at infinity, GPE is actually equals to 0, so KE is greater than 0, and this makes sense, it checks out. So in the end, what you can understand from the energy considerations is that bound orbits, it can never have the object go to infinity, because if the object were to fly off to infinity, then KE wouldn't make sense. So this is it's sort of proof, it's sort of a contradiction in a sense. So it cannot be at infinity. So bound orbits, the object never goes to infinity, whereas unbound orbits, the object can go to infinity. So that also shines light on what bound and unbound means. Yeah, so I hope that clarifies some stuff a little bit. So okay, then number 2 for ellipse properties, ellipse have two foci, so I'm not really sure how crucial this is for H3, but generally some important properties of ellipse is that they have two foci. This is studied under conics. Okay, there's conics, and there's an eccentricity number. I believe that eccentricity of ellipse, I believe that is less than 1. So eccentricity denotes how flattened the ellipse is. So yes, the eccentricity is always less than 1. Whereas for other conics, the eccentricity can, so this kind of classifies it. So we have over here, see, eccentricity for parabola is equal to 1, for ellipse is less than 1, and for hyperbola is greater than 1. And for the circle, I believe it's equal to 0. Yes, so that's something to note about eccentricity. So yeah, this eccentricity, it's in conjunction with flatness of ellipse. And okay, so that's property number 1. So property number 2, angles. So when you bounce, let's say you shine a light ray from the foci onto any point on the ellipse, right? If you follow the law of refraction, let's say let's say the ellipse is a mirror, then the other light ray will always bounce to the other foci. So basically this angle is always equal to this angle, and that applies for any point on the ellipse. Okay, so that is angles. And there's a very cool exhibit at Science Center that demonstrates this. You try to flick a carom such that it doesn't hit the other foci, and you find it's very difficult. So lastly is lengths. So for ellipse, right, the sum of lengths from D1 to D2 is always going to be constant wherever this point D is. So you can move this point around anywhere on the ellipse. D1 plus D2 is constant. And in fact, definition of ellipse, in fact that's the way ellipses are defined. You can see that so there's this picture of people putting two pins and then putting a fixed length string, so the string cannot stretch, and then they use a pencil to draw the ellipse. So that's one way the ellipse is defined. There are other equivalent definitions, such as slices of a cone as well, but this is so okay. So with that, so I think I'm done with talking about ellipse, and I believe I've already spent 15 minutes. Okay, so let's go on to the next question. Gauss law for magnetic fields. Okay, so Gauss law for magnetic fields, there are, to answer the question directly, it's closed loop integral of B dot dA, closed surface integral of B dot dA is equal to 0. So what does that mean? Okay, I'm thinking whether I should okay, let's read out B and C first. Okay, so explain why the magnetic field lines always form a closed loop. So okay, so before I talk about that, this is something called it's something defined in vector calculus. So if you want to find out further about it, this is vector calculus notation, and it's very important in physics. I'll talk about it more later. So because magnetic monopoles always exist in pair of north and south poles, and there are no magnetic monopoles, the field lines that originate from the north pole or magnetic dipole will always enter again at the south pole, thus forming closed loops. So explain why the existence of, so you can read answer by yourself also, is basically because there are no magnetic monopoles, and hence so I'll explain this entire question together as an entirety. So question 2, right? So question 2, let's answer the question 2. So first thing I'll talk about is vector calculus, and second thing I'll talk about is magnetic monopoles. So the first thing is to help you understand the equation here. So what in the world is this equation? Okay, so there are a few things to understand over here. Is that we understand vectors, right? Vectors are pairs of are triplets of numbers. So vectors is like 1, 0, 0, right? And then there could be another vector, let's say 1, 2, 1. Okay, so these are vectors, and we understand there's a dot product here. So there's a concept of vectors, and then there's a concept of dot product. So dot product is, we know that is a dot b equals to a. So a dot b, if they're vectors, then is equals to ab cosine theta, right? So these are magnitudes and these are angles, and they, in a sense, they illustrate how much two vectors are pointing in the same direction. So if theta equals to 0, then you see that they in a sense they point in the same they do point in the same direction, and the dot product will be maximized. Whereas if the theta is in if theta equals to 180, then they point in opposite directions, and the dot product is negative. So that's the dot product over here. It's precisely the notion of dot product. And what is this dA thing? So this is where it becomes a little bit challenging, because we're talking about surfaces here. So maybe instead of talking about dA, first I talk about the surface. So what in the world is this weird curly sign, integral sign with this ball here? It is actually called a surface integral. So you might see some books, they write it in terms of 2 circles. So they might write something like I think they write something like that, yeah. So anyway, what is a surface? It's a 2D, think of it as a 2D sheet embedded in 3D space. So we know we live in 3D space, right? So we live in 3D space with x, y, and z coordinates, right? So a surface is basically imagine some sort of sheet. So some sort of closed sheet. So it's like a balloon. So it's like a balloon. Okay, you blow up the balloon, and then because it's made out of rubber, you can deform the balloon in any way you want. So you can think of it as a deformed balloon, right? And so it's sort of like a ball. Okay. And what is this integral? So what is this integral? Actually, this thing is called a surface integral. So this notation over here is a surface integral, and once again it goes back to vector calculus. If you want to study the study of vector fields and stuff, then you're going to need to study vector calculus. There's no running away from it if you want to understand physics. But surface integral is doing the integral over the entire surface. So you know how if you integrate over a real line, let's say you integrate from a to b, right, f of x dx. So you have if this is the real line, then you have if this is the real line, okay, then you have a, and then you have b, and then you have f of a that runs f of b, and then you integrate, and then it's the area under the curve, right? So one way to understand the area under the curve is thinking of slicing this line from a to b, in terms of many small segments dx. So you label this as dx, and in the limit of infinity you shrink it down to 0. You shrink it down to 0 size, and for each one of them you calculate a small rectangle, and so what's the area of the rectangle is going to be f of x dx. f of x dx. So this is the area of the rectangle over here, and you are essentially, from integral from a to b is essentially a sum from a to b. Yeah, so in a similar sense, comparing to the surface integral we have over here, imagine a 2D sheet, right? Then you're trying to integrate over the surface. So when you integrate over this function over here, you're integrating over a real line. Whereas in this surface integral, you're integrating over a 2D surface. So this is a 1D integral, and this is a 2D integral. So now instead of thinking of dx, right, you now think of a small area dA, and this dA, it could be written as dx dy, right? If let's say you're talking about lengths and heights, right? It could also be written in terms of polar coordinate if you're talking about some sort of polar surface. So that would be r d theta, or there's other coordinate systems, and really all this goes into differential geometry stuff, which is even more advanced than vector calculus. But if you want to understand vector calculus, there's some great Khan Academy videos. I think they're the best, Khan Academy. And if you want to understand physics Olympiad, go further. Vector calculus is quintessential. You cannot get rid of vector calculus. So if you want to study higher physics, you might as well learn vector calculus right now. And don't be afraid. It's not that daunting actually. So so anyway, going back over here, so you integrate over the surface. This is sort of a surface integral or surface sum. By breaking the entire surface, the entire balloon, down into small tiny chunks, then we sum over each of the tiny chunks. So now b dot dA, what is b dot dA? B is a vector, and dA is also a vector. So this is just a scalar. So it's a scalar function, and we integrate over the scalar function. That makes sense, gives you a scalar, a number. So what is B? So B in this case is actually called a vector field. So B is a vector field and represents the magnetic field. So actually in electromagnetism, I'm getting very carried away here, but in electromagnetism, B and B are both vector fields, right? And then you, on top of having vector fields, you have scalar fields. So what are scalar fields? So you can think of vector fields as attaching every point in space with a vector. So that's the idea of fields. So you have also scalar fields, where you have phi. So like for example, the potential, the electric potential is a scalar field. So and you can get a vector field by taking the gradient of a scalar field. So this is called gradient, GRAD. You can search it up. It also appears in vector calculus, but I really don't have time to talk about vector calculus in this video because it's really getting very long. So anyway, so when you take a vector field dotted with a vector, then you get a scalar function, and that's essentially what this is saying. So all this fancy math, what does it really mean physically? It means that if you have okay, it's kind of funny that after all this, then I get onto the physical interpretation. I think the video is really way too long, but I guess I'll go through it slowly. So what does b dot dA equals to 0 mean over the integral over the surface? So it means that if you dream of any surface, right, you dream of any balloon, okay, and you think of this as a 3D object, okay, it's kind of like a 3D balloon. Then you put inside the 3D balloon, you put some sort of magnetic poles, okay. So you put a magnetic pole or whatever magnetic these are sources of magnetic fields. Sources of Oh crap, the problem comes again. So we put in sources of magnetic fields. So you put in sources, right? I'm so sorry. So you put in my pen is not working. Oh damn it. Okay, there we go. So I'm so sorry for this crappy video. So we put in sources of magnetic field, and just like electric charges, these sources they radiate they radiate magnetic field lines. Okay, and these magnetic field lines, they'll be, since there are many sources, they'll each have their own magnetic field lines, and as a result, the magnetic field lines at any point is going to be the sum of the contribution of these three magnetic sources. So let's say this is the contribution from the first one, this is the contribution of the second one, and let's say the third one contributes something like that. So you add these three vectorially by the principle of superposition. In a sense, this tells us that EM is a linear theory okay, and then you get a net magnetic field. So in this case, you probably get some net magnetic field like that. Okay, and what this is trying to say is that whatever magnetic field configuration you have, if you have any surface at all, you can choose any surface you want, and then you sum the magnetic flux flowing through this surface. This is the magnetic flux, right? You sum the magnetic flux flowing through this entire 2D surface, you will get 0. It necessitates that you get 0 no matter what surface you have and no matter what magnetic field you have. And so that actually places a great constraint, right? Because if you just think about putting a single charge inside this, thing, then it's going, let's say it generates magnetic fields that points outwards all the time. Then essentially the flux flowing through this will always be net positive. So if we put monopole, then integral of B dot dA is not equal to 0. It's clearly going to be greater than 0 in this case, or it could be negative, but it's essentially not 0. So if we put a monopole, then this law does not hold anymore. So, but the fact that this guy called Gauss said that this rule must hold, that means there must be no monopoles. So that is essentially the consequence of Gauss' law for magnetic fields, is that magnetic monopoles cannot exist. So I hope you caught the argument over here, because what I'm trying to say is that Gauss' law says this is true, and then we say that if there is a magnetic monopole, then this cannot, it will break down the equation, because it will not be equal to 0, and that violates Gauss' law. So hence, there cannot exist magnetic monopoles. So that's essentially the statement of Gauss' law in this case. So yeah, so then as for part B, why magnetic field lines always form a closed loop, is because there are no magnetic monopoles. So any so-called positive monopole, right, it must be accompanied by a negative monopole very nearby, because you see, right, any positive monopole, if right, is physically separated from a negative monopole nearby, then we can always draw a surface here encircling the positive monopole, and as a result, Gauss' law will not hold. So essentially, what this is saying is that the positive monopole must be right beside the negative monopole, such that you cannot insert such a surface. And this might not really make sense, but if you think of shrinking the distance between these two to 0, so the distance goes to 0, then what you have essentially formed is a dipole. So this is now a dipole with a positive and negative. And now the dipole, what is this few lines going to be like? The positive is going to be shining out, right? And the negative is going to be sucking in. And as a result, the few lines that's going out must always come back in, because if it didn't, then you can always draw a Gaussian surface that causes the violation of Gauss' law, right? Imagine if there's one line that went out that didn't go back in, then we can just encircle the entire thing, and there we have it. We have a escapee. This guy has now escaped. This magnetic line has now escaped and caused a net flux. So it caused some sort of flux to be out of the surface. So that's why magnetic field lines always form closed loops, because it's a consequence of Gauss' law. So you can explain it in terms of words like that, but this is the idea and my 2 cents opinion on how I logic this out. Yeah. Okay, so explains the existence of monopoles inconsistent with Gauss' law for magnetic fields. Yeah, because if magnetic monopoles exist, then magnetic field lines originate from it, and we enclose this point and perform the integration, then clearly the integral is not equal to 0, and hence that violates Gauss' law. So that makes sense. Okay, so I think I'll do one more question before calling the end of the video. Yeah, so state the line integral form of Ampere's law. By the way, I have the answer keys for this paper, so if you want it, please feel free to email me or message me, and I'll be happy to send it to you. So what is Ampere's law? Actually, the one that we are taught, or rather the one that in the answer key, is this. But I'm gonna go digress later on. So essentially, this is telling us that when you have a current carrying loop, it's going to generate a magnetic field. Okay. So it's I enclosed. So yeah. So define the symbols used. So okay. So first thing here is a line integral. Later I'll talk about that. It's also similar to the surface integral. Then we have all these definitions over here. But it's that. Let's talk about it. Let's digress a bit in conjunction with the definitions. So what is the thing over here? Alright. So first thing we have is a line integral, right? So just now I talked about surface. I talked about a balloon, right? Some sort of balloon, some sort of surface integral. But now in this case we don't have a surface anymore, we have a line. So this is just a circle. It's a circle. It's like a rubber band. You can think of it as a rubber band. And so this loop, it can be stretched, it can be deformed. So instead of having a perfect circle, you can have something like that. Any line integral works. So Ampere's law appears for any line integral. And what does the line integral say? It says b dot dl is equals to mu naught I. So what is this left hand side first? This left hand side is again a dot product. dl is going to be a small distance tangential to the Amperian loop. So what does that look like? That looks like, if this is our loop, right? If this is a line integral, then this dl is going to be like this. So essentially dl is, imagine of this like, it's sort of like it's a little man walking along the Amperian loop. So from his perspective, he's just walking this length, right? So in the Amperian loop later it closes up, but for now he's only seeing, he's short-sighted, so he only sees this dl, small element dl. It's sort of like a dx kind of thing. In fact, if you parameterize it in terms of certain coordinate systems, then you do write it in terms of dx or like something like rd theta or something. Yeah, so that's what the dl is. And so once again, to really make sense of this, you always have to turn back to vector calculus. There's no running away from vector calc in I can't spell. Okay, you get the idea. Vector calculus. There's no running away from vector calculus in physics. especially in electromagnetism. And so what does this value equal? So Ampere's law says that this value is always going to be equals to mu naught I, where I is the current that's penetrating through this loop. So what does this look like? So Walter Lewin has this wonderful video. Yeah, he draws this diagram. You see that Walter Lewin draws this diagram, right? So this curly thing over here is a loop, right? And then this is a surface that you attach to it. So the current is the current that penetrates through this surface. So once again, if you want to understand electromagnetism, 802 X MIT Walter Lewin is the best at explaining it, and he's the one who helped me understand all this, so I strongly recommend watching his videos. So anyway, so anyway, this is, so imagine you have a Amperean loop, right? So let's say this is Amperean loop, and then so this is a loop, and then you have a wire that goes and it penetrates out. So you see that there's a it's like sort of like a plastic bag. So this is a plastic bag. So this is a loop attached to a sheet or surface. It's a loop attached to a surface, and this is a plastic bag. So you have a plastic bag, and then you have a wire poking through the plastic bag. You realize that no matter how you twist the wire, you always have to penetrate through some point. And this, if you count the current, this is called I enclosed, or another better phrase for it is I penetrate. It's the current that's penetrating through the Amperean loop attached to the surface. So essentially that is it. So this current is a way of quantifying how much current flows through this Amperean loop, and this Amperean loop is precisely the integral that you perform. So in this case, whatever Amperean loop you choose, this law must hold. So we can choose this. In these vector calculus laws, there's always a very big degree of freedom, a lot of freedom you can choose in what Amperean loop you want to choose, and depending on the Amperean loop, you can get varying degrees of utility. So for example, later when we're talking about the straight copper wire carries current I, later when we're talking about this current, then we'll see that the choice of the Amperean loop, if it's a circle around the wire, then it's very useful. Whereas if it's some weird shape, perhaps like that, then it's going to be not useful. And this looks like a duck. So so we have the one key idea in electromagnetism in Maxwell's equations is that you have a lot of degree of freedom to choose these lines and surface that you integrate over. However, because this must hold in all of space, right? Actually, there isn't that much freedom, because if you then, okay, so digression. Although this entire video is pretty much a digression, but because it must hold for every single loop, you imagine that breaking this loop down into many small loops, right? And then if you break this loop into many small loops, and then you sum all of the small loops up, you get the result of the big loop. So this is also something called Stokes Theorem, and there's and as a result, actually you can convert all these loop integrals and convert it into a small loop. In a sense, you can convert the equations into a very small loop, and you end up getting curl. So you end up getting a condition for the curl of B. Yes, but this is owing to Stokes theorem. So once again is vector calculus. I cannot stress enough that vector calculus is the language of electromagnetism. So anyway, you choose a loop integral and then you count this thing, the current that's flowing through the loop, it must hold true. So that's essentially Ampere's law. So yeah, so now we have a long straight copper wire of radius r, and we want to show that the magnetic flux at the distance d is this. Okay, so okay, so so what this is saying is that there's a current carrying wire of radius r, and it has current I flowing through it. Current I flowing through the entire wire evenly, I suppose. Yeah, so okay, so if you want to choose, so you want to use Ampere's law to show that the magnetic flux density at distance d. So if you have distance d away from, so this cylinder, right? This cylinder is going to have a line through the center. It's going to have and distance d away, you want to measure the magnetic field strength. So so the magnetic field is a vector, right? But we in a sense, the magnetic field is a vector indeed. And so okay, I'm a bit hesitant to jump into the direct calculation of this, because actually it's as simple as 2 pi d times b equals to mu naught I, and then you just rearrange. But I'm going to go into a digression again and share with you why our seemingly complicated b dot dl suddenly reduces to something so simple as a multiplication. And yeah, that's the thing. So actually this b, right, you might be wondering, first question, right, is b is a vector. How come over here we don't see any vector notation at all? Well, that is because this is actually the magnitude of b. And number two, if this is only the magnitude, then what is the direction? So it's actually going to be tangential to the circle that we draw. So essentially, if this is d, then if this is the point we're querying, then it's going to be like this, right? Such that this is perpendicular. Okay, you need to imagine in 3D. And if let's say we are asking for another point, here, then it's going to be perpendicular as well. And essentially this around the entire circle, right? Imagine drawing the entire circle around the loop. At any point, the magnetic field is going to be tangential to the circle. Yes, and how do we know? So the direction of vector is tangential. And how do we know? We know because of Biot-Savart. But so I think it's time to digress into Biot-Savart. So Ampere's law is one of Maxwell's equations, and for some of you, you might know of something called Biot-Savart as well. It's the law that dB is equals to I believe mu naught over 4 pi I dl cross r over r squared. Yes, this is Biot-Savart law, and if you want to see a derivation, I have made a video on it before. I believe it is called Relativistic Electromagnetism. So Relativistic Electromagnetism is a video I have that derives Biot-Savart from Ampere's law. So in a sense, Ampere's law is more universal, and Biot-Savart's law is a way of calculating the magnetic field more easily in a different representation. Yeah, but it's a bit of a long road to go from Ampere's law to Biot-Savart. But just know that there are two correct ways of calculating magnetic field. So Ampere's law is particularly useful when we consider symmetry, because the reason why we can pull out this 2 pi d times b is because around the circle, right? Around the circle, the entire system has rotational symmetry precisely because this copper wire is a cylinder. So if you rotate the entire system, the magnetic fields should not change because it's exactly the same setup. That means we know that the magnetic field is constant throughout the entire circle. So that turns this integral, when your b is inside the integral and when your b is constant, right? When your b is constant, then you can essentially pull it out. So then you end up having a loop integral of dl. So your loop integral of dl is actually simply 2 pi d, where d is the radius. Yeah. So that is why we can essentially write it this way. If we chose some other loop without rotational symmetry, let's say we chose a loop that instead of going like that we had something like that, then the b here would be different, the dl here would be different. It will still satisfy Ampere's law, definitely, because it must hold. Ampere's law must hold by axiom. But it will still hold, but it will not be a useful choice. So this is a useless choice of Amperean loop, and we cannot calculate it easily. So it's something like we don't know how to calculate for it, but we know it's true. Yeah, we know it's true by essentially a theorem, a law. Okay, so that is essentially what I have to say. And number two, I was going to say something else. So I was going to say, what if wire is not infinite? What if the wire is not infinite? Because you see the I enclosed penetration, right, is assuming that the wire is infinite, right? I mean, if the wire was not infinite, in the case of, let's say we had this, and then let's say the wire terminated, okay? So and then we have Amperean loop like that, right? So of course this wire flowing through, the current flowing through the wire here, it would generate some sort of magnetic field. It would generate magnetic field around this Amperean loop, and the integral of b dot dl is not equal to 0. But you see in this case, then your choice of the surface that you attach to this Amperean loop is going to get different results. If you choose the surface that attaches the Amperean loop to be very small, then yes, there is an I penetration that's not equal to 0. Whereas if you choose another choice of Amperean surface, then your I penetration is equal to 0. So how do you resolve this conflict? So it seems that Ampere's law depends on the surface that we attach. However, one must note that this is the Ampere's law. Essentially the Ampere's law written here is not complete. There's actually a additional term over here. So what is the full Ampere's law? It's actually mu naught I plus mu naught E naught integral of E dot dA. Change in time E dot dA. So, and this is over the same, this is a surface and this is a loop. So this is the Amperean surface that you attach. So this surface over here, right, this surface over here is precisely this surface over here. You're doing a surface integral. And what is this dE dt? How does it account for this situation? We see that if let's say we chose the outer Amperean surface, then when when the current flows like that, right, and it just halts here, then there'll be an accumulation of charges. And accumulation of charges is sort of like capacitor, so you end up creating there's charges here, right? And we know charges, they create electric fields. So charges cause electric fields. So this is an E field would then, because you accumulate charges, your E field would be increasing with respect to time. And that is exactly what this E dot dt captures here. So this is a term that fixes Ampere's law. And in fact, a bit of history, Ampere's law is this, right? But Maxwell was the one who discovered that, hey, actually we need this additional term over here. So that's the contribution of Maxwell to Ampere's law. And yeah, and okay, another book that I heavily recommend is David Morin for EM. Some say Griffiths is good, but I personally don't read Griffiths. So yeah. Okay. So I've digressed quite a lot now. I think maybe I have to split these papers into like 4 or 5 videos perhaps. So yeah. Okay, so over here, this is the case where, let's go on to part 2. So this is the case where D is greater than R, right? And we know it's something like that. So we can draw it. So it looks like that. So this is the region where D is greater than R. And what is this value? This value is mu naught I over 2 pi R. Then what is in this region? Okay, we need to choose the Amperean loop to be inside the thing. And then we realize that what's the difference over here? The difference D is this is still 2 pi D, but the difference is that less current flows through, because now instead of all the current, if the current, let's say, it flows through evenly, this so we're talking about a current density JDA. Okay, so current density, the units of current densities is ampere per meter squared, is current per unit area. So if we're going to have a smaller Amperean loop, and this Amperean loop doesn't encompass all the current that is flowing through it, then the current will be less. And how much less would it be? It's going to be this is going to be less by a factor of D squared over R squared, because you're taking the area. So it's pi D squared over 1 pi R squared, but pi cancels. So if you rearrange, then you just get, rearrange this, then you just get B equals to mu naught I D over 2 pi R squared. So yeah, R squared is a constant, the rest are constants as well. So D is the only variable here. We're plotting with respect to D, so we're going from D equals to 0, B is equal to 0, then we see that it varies linearly. So this is yeah, that's what they're looking for. So okay, I think this is the last question I'm going to be going through before I call it a night, because my throat is kind of tired. So explain in the presence or otherwise of a magnetic field inside the wire. Yeah, so okay, because I have the answer key, and this is an open-ended answer, I forgot to write it out, but I'll just type it out right now. So I've more or less explained explained in the previous part. If we assume that the current density in the copper wire is uniform and given by I over pi R squared. So the assumption that the current density in the copper wire is uniform is important. Then any Amperean loop within the wire will enclose some current. This in turn explains why the magnetic flux density within the wire is non-zero. So basically what it's saying is that, as I've previously already drawn, if you have a, because the wire has some thickness, okay, wire has some thickness, right? So if this is the center and you have a distance d away from the origin, then the magnetic, assuming the magnetic, assuming the current density, which is equals to I over 2 pi r, no, sorry, 2 over pi r squared, is constant, is uniform, then the total, imagine how much current is flowing through this Ampere loop over here is going to be pi d squared times j, right? So okay, perhaps as a closing remark, I will perhaps elaborate a bit on densities. So let's start off with charge densities, okay, because it's similar to current densities. So charge densities, for a point charge, right, we know it's easy, it's just Q. So the unit of a zero-dimensional point charge is just coulombs. Then if you have a line charge, right, so line charge, you have a line charge, then you might see something like lambda. Usually the symbol is lambda and it's a function of x. So x represents a coordinate along this line, right? So x represents a coordinate along this line, and the charge density, the most useful thing to look at when you're considering charge densities is the units. So the units tell us a lot about what we need to do with these densities in order to obtain a charge. So you see that if the units of line charge is coulombs per meter, right, then we need to multiply by a distance. We're missing a distance of sorts. We need to multiply by a distance in order to get charge. So what might this distance be? So this distance is dx. So let's say we have x, right? Let's say we have x at a point, and then a point away we have x plus dx. So dx represents a very, very small distance, and this length is dx. So then your charge, right, dq, the charge that is the total charge of this small line dx is going to be lambda x dx. So you see that if you consider the units, this is coulombs per meter squared, dx is meter because x is a length and d is unitless, and this is just coulombs. So coulombs equals to coulombs per meter times meter. So this is the expression that we currently obtain for in order to if we want to do something like integral. So then so pedagogically, let's say we have a line charge, and then let's say we want to integrate, right? Let's say we create some potential. So you say potential equals to integral of dq over 4 pi epsilon naught r. It'll be a minus sign. So that is essentially what integral does. If you want to you want to find the total, let's say total electric potential, right? So okay, maybe total electric potential at a point due to a line charge is going to be equals to sum of many small contributions. Each one of these small contributions of length dx is going to contribute a certain d phi. So it's going to be integral of d phi over the entire line charge. And what is d phi? Each of the d phi is going to be equals to minus dq over 4 pi epsilon naught r, where r is a distance. So r is the distance from this line charge thing to the point of concern. So then we write it. So this is essentially, this took me a while to understand as well, but this is essentially how you do integrals in physics. You think of units and you write things like dq, d phi, and then you eventually turn them into a mathematical problem. So using dq equals to, using this relation, we can then know that this is dx over 4 pi, if I'm not, then let's say it's radius r away, so we know that this is r is going to be r squared plus x squared, okay? And now we have turned the integral, remember we integrate over line, right? So when you integrate something, integral is always paired with a d something, okay? It's always paired with a d something, and the something over here will determine what goes into the integral. So over here, d phi, we don't really know. I'll just write it as something like line charge. dq, I'll also write integral over a line of dq. But as soon as you get something like dx, right, this is now a coordinate. So I guess this is sort of like vector calculus. Perhaps I'll do a complete tutorial on integration in physics, because this is something that requires quite a lot of practice to understand. It always seems very daunting, you know, what kind of integrals are you doing? But yeah, perhaps I'll do actually, yeah, this is a very good video idea. So upcoming video idea of integration in physics Olympiad. So yeah, so once you have a coordinate, then over here in the limits of integration, instead of putting line over here, you essentially substitute in the limits of integration. So if your integrals are your limits of integration is, let's say, minus a to some b, then you put in minus a to b, and that depends on your coordinate over here. And essentially that is all there is to integration in physics. One thing to note is that when you do a change in variables, let's say you do a u substitution in your integral, and you say you change the dx in order to change it to du, then your du is a new coordinate now, and now you need to substitute in the new coordinates of integration. So that is a small digression from charge densities, but I get quite carried away, I'm sorry. So anyway, going back to it, if you have a surface charge density, so surface charge density, then it's 2d, then it will just be coulombs per meter squared. And then if you have a volume, right, volume charge, then it will be 3d, and it will be coulombs per meter cubed. So in this case, you need to multiply by dA, which could be equals to like dx and dy, and in this case you need to multiply by dv, which could be like dx, dy, and dz. Or if you're looking for more exotic ways, right, then we could be talking about stuff like spherical coordinates, and this dx, dy, and dz is essentially where you can change your variables in order to be like del in cylindrical coordinates. So we're talking about dv in terms of here. So you see, this is differential displacement, right, in 3 different coordinate systems, and then you have differential normal area. This is the dA just now. We do a Gaussian integral, right? When you do your integral b dot dA, this is your dA. So you have different coordinates as well. And lastly, dV. So this is related to something called differential forms, which is very interesting also. But I think I'll cover more of this in my integration for physics video. So it's quite long now. Yeah, shout out to Matthew. No, sorry, shout out to Ethan for sending me this paper. And hi Ethan, you're probably watching this right now. Yeah, so yeah, that's all I have to say. Okay, let me drink some water. Okay, it turns out that I had originally intended to make videos teaching or going through the history physics paper because this year my batch has quite a lot of students, and I think some of them are struggling, so I want to help these students. And if you're one of those students, please feel free to email me. I'm happy to help. But originally I wanted to go through, but then I think perhaps what I'm doing right now is better than just purely going through, because I'm digressing a lot, but I'm also covering a wide variety of concepts, and in the end, if you want to excel in physics, you need to have a global understanding of the whole picture. So it slowly accumulates. Yeah, keep practicing. But this video did not turn out the way I expected it to, so please give me feedback if you want these type of videos, because the purpose of this video is really to help history students improve. I don't want to be just blabbering useless information. So please feedback to me how I can best teach, because I also don't want to purely go through content, because the teachers have already done that at school, and I also don't want to purely go through the paper like uh, like what the teachers do in tutorials, because I think that way I don't really value it that much. So but as a result, as I'm trying to strike a balance between these two, um, going through content, I end up digressing a lot and spending 1 hour on just 4 questions. So yeah, please leave a comment, and or if you're shy, email me, tell me if it's helpful. I really don't know if the outreach will be good. um, I don't know if many people will even see this video, or whether they probably click away by then. But yeah, tell help me help you, basically. I want to help you understand physics better as a history student. So yeah, if not, that's all I have for today. mm, I look forward to making this integration in physics Olympiad video, where we can calculate we can integrate stuff like moment of inertia, charge densities. We can calculate potentials, electric fields, and many other things. So we can discuss things like different coordinate systems, what happens when you change the coordinate system, what does it really mean to do an integral. We can talk about differential forms. mm, and yeah, that's pretty much it. We can talk about probably a bit of symmetry as well. So yeah, have a nice day. Bye.